asked, what X-ray interaction with matter does the X-ray photon behave like a wave? What would your answer be?
Coherent?
Coherent. And why do we say it behaves like a wave? Why is that? Why is it more like a wave? Think about what it does to the atom.
Because it vibrates it and doesn't lose energy?
Right. It vibrates it. Right. It vibrates it. And the atom is not ionized. And the scattered photon still has the same energy that it entered the atom with. Right. So it's a wave-like property. Now, we just finished Compton. Compton, can it cause ionizations? It does, right. Compton causes ionizations. So if you think about wave-particle duality, how would we say the X-ray photon interacts with an atom if a Compton interaction occurs? How would we say that X-ray photon has behaved because of this interaction? More like a wave or more like a particle?
More like a particle?
More like a particle. So that's why X-ray photons are classified as having wave-particle duality properties, because at the lower energies, the X-ray photon acts more like a wave, and it only causes atoms to vibrate. But with intermediate energies and higher energies, then it acts more like a particle, like a bundle of energy that can knock electrons out of their shells. So with a Compton, it acts more like a particle. And the same thing is true with photoelectric. So with photoelectric, this also consists of what we classify as intermediate energy photons, greater or equal to 15 keV. Okay. So if an inner shell electron is knocked out with a photon that has 15 keVs or greater, it's a photoelectric effect. Okay? So what happens here is the inner shell electron, specifically the K shell electron, is knocked out. And when that happens, it takes all of the photon's energy to do that. So we get total photon absorption. So the photoelectric effect results in complete photon absorption by that atom in the patient's body. So that atom has absorbed all of that energy because it took all of that photon's energy to knock out the inner shell electron. Okay. So this is what it looks like. Have the incident photon coming in, and it hits that K shell electron, and it knocks it out. Notice the name that's given to an electron that's knocked out it's referred to as a photoelectron. That's just what it's called. So the incident photon comes in, and it knocks that electron out of orbit, which creates a void, a vacancy. This probably, or hopefully, will look very familiar to you. Although you have to remember, this is taking place inside of the patient's body. But what does this look like? We talked about it last week.
Like X-ray production.
It looks like X-ray production, right? Well, essentially, this is X-ray production inside the patient's body, okay? So the X-ray photon comes in to the atom, knocks that K shell electron out of orbit. Remember, atoms do not like to have the inner shells missing. They're very unstable. So whenever an inner shell is missing, another shell will drop and fill the void. So an electron from another shell will drop and fill the void. So in this case, an L shell is going to drop and fill that K shell void. Well, what do we know about the shells? What do we know about them and their binding energies? Is there a difference in binding energies between every shell? Yeah. So if L drops to fill K, the difference in binding energy is given up as an X-ray photon. So we actually get X-ray photons being produced inside of the patient's body from this photoelectric effect. But there is a change in direction. When that energy is released, when the L shell drops to fill K and that difference in binding energy is released as an X-ray photon, the direction is different from the direction that the original photon came in. So it's classified as a scattered photon. Another name for it, you may hear it referred to as secondary radiation. Scattered photon, secondary radiation, same terminology. We tend to use the term scattered photon more so than we do secondary radiation. But just know that scattered photon and secondary radiation are synonymous in this case. The reason it's called secondary radiation with this photoelectric effect is because it's an X-ray photon that was not produced at the tube. X-rays that are produced at the anode are referred to as primary radiation, but X-ray photons that result from the photoelectric effect can be classified as secondary radiation because it's radiation that was formed inside of the patient's body. Okay. But nonetheless, it's a scattered photon. So as far as the patient's concerned, there is a potential for biological damage because an ionization has occurred. In terms of image quality, as far as image quality is concerned, the photoelectric effect does provide the image with the useful information. The fact that the photon is absorbed by the patient's body yields itself as the white areas on images. And we'll be looking, more at this, but the photoelectric effect is what provides the white areas on an image. So for example, bone. The reason bone shows up, and bone will show up white on an image, but bone shows up white because of the number of photoelectric interactions that take place. So the fact that the bone absorbs that photon energy allows for the bone to be visualized, and it shows up as white areas on an image. Okay. In terms of the scattered photon here, the energy of this is so low, it typically doesn't even make it out of the patient's body and impact the image receptor. Okay. So even though a scattered photon is produced, it just really doesn't have an impact on the image, as far as a detrimental impact, as far as making the image gray. The significant contribution here by the photoelectric effect is the fact that this photon is completely absorbed by the anatomical structure, and it will show up as a white area on the image. Okay. So although, this ionization event can potentially be harmful to the patient because of biological impact, we need this type of interaction to take place because it does provide useful information on the radiographic image.
A question.
So
the energy of the photoelectron that got kicked out by the photon, is that equal the energy of that photon?
Oh, how much energy does the photoelectron, how much energy does this have?
Right.
Very, very little. This will retain very little energy, typically.
So is there any vibration, or I'm just trying to understand what happens when it absorbs all the energy and the photon kind of no longer exists?
And the photon no longer exists because it gives up all of its energy. It just gets absorbed by that photon. By the atom. Some of it is imparted to the photoelectron. Well, I shouldn't say sometimes it's little. It depends. It depends on your particular atom. Sometimes this can have quite a bit of energy. There can be a slight vibration in the atom when that energy is absorbed. but it's not a vibration like you have with coherent, and then that energy gets released as a scattered photon. Here, the energy of that scattered photon is coming from the fact that there was an ionization event, and we have a change in binding energies here. So that atom, basically, it just absorbs a bulk of that energy. It's absorbing it through that ionization process. Okay. Does that help a little bit? There is more detail to it. It does go deeper than that, which I can give you some references or talk to you about that if you want to at some point.
Yeah, I just wasn't sure if the photoelectron would then go on to create, X-ray photons in other atoms. But if it doesn't really carry much energy, I'm assuming that doesn't really happen.
Well, the photoelectron, typically what it does is it could go to the atom next door and it could fill in a void from an ionization event that was caused by a different X-ray photon. Okay, because remember, what's causing the photoelectric effect here is a photon. This is an X-ray photon that has come out of the X-ray tube. And when this photoelectron is knocked out, this electron can go to an atom right next to it. And, maybe there was a Compton interaction that took place, and this photoelectron could settle into an outer shell electron void. Okay. But this photoelectron isn't going to go on and produce X-rays. It'll settle into an electron shell where there's a void. Okay, and this X-ray photon is gone because its energy has been totally consumed, totally absorbed by the atom, because it took all of that energy to knock that photoelectron out. So it gave up all of its energy. Okay, so you will get a little bit of heat being produced in there. But chance for biological damage because it's an unstable atom now. Now there is a chance that photoelectron could drop into a K shell in an atom next to it that underwent a photoelectric effect. Okay. All right. So if you're asked on a test what two interactions with matter cause ionizations, what two would you say?
Compton and photoelectric effect.
Okay, Compton and photoelectric. Which